and Ramon Filgueira, who will speak to you today from different associations, from different institutions, and they will speak to you about carrying capacity as it affects shellfish. And so you'll just have to advance that button.
Yeah.
I don't have a clicker.
Just
Thank you.
yeah, the whole concept and the research on carrying capacity. There's been quite a number of people in sort of the Maritimes that have been working on this topic. There's probably been more work on carrying capacity in the Maritimes than in just about any other place in the world. And so for just one of us to come up and talk about it, it's a little difficult. So we're going to do a bit of a tag team. Myself starting out, and as I mentioned before, I'm with Fisheries and Oceans Canada. I'm the head of the Habitat Ecology section of the Coastal Ecosystem Sciences Division, and it just goes up from there. And I've been working on shellfish for my entire career, which is now 38 years and going. I've been working exclusively on aquaculture issues for the last 20 years, primarily shellfish, but more recently getting into finfish issues. And the other two are both here in the center table, Thomas and Ramon, and they can introduce themselves as they come up. So basically just a quick overview of what I'll be talking about, what we'll be talking about is, first of all, I'll start just talking about what is carrying capacity and how that interacts with the pelagic environment, how we measure some of these pelagic effects of the shellfish culture. Then I'll talk a bit more about the benthic, the organisms on the seabed interactions with the shellfish culture, and then talk a little bit about monitoring benthic effects. Then Thomas will talk about more of the physical side, hydrodynamics, and how that interacts and basically determines carrying capacity and water circulation. And then Ramon, who is also a modeler, like Thomas, will be talking about how you integrate these concepts of carrying capacity into management and how they model the aquaculture environment interactions, and finish off with some work on ecosystem health monitoring based on modeling. So first of all, what is carrying capacity? It's one of these things we have a bit of an intuition of what it means. Of course, scientists make it more complicated by giving it a whole bunch of different definitions, but the four types that we're talking about is first physical carrying capacity, and that's basically related to the physical needs of the species that you're working on, the salinity, the temperature, what do those organisms need, but it's also the limitation of space. It's how many can you fit in to a particular area. Production carrying capacity, this is one that's most interesting to industry, really. It's the stocking density of shellfish at which the harvest is maximized. And we'll be talking a fair bit about production carrying capacity. Ecological carrying capacity is the next step. It's the stocking density that you put in which causes unacceptable ecological effects. And so it's this word unacceptable that creates some difficulties in determining what the ecological carrying capacity is. How much can you put there before society says, well, this is unacceptable? And it's not really even a science issue. It's more of a society issue to determine what that is, although science helps to inform that. And finally, social carrying capacity, the level of farm development that causes unacceptable social impacts. It goes beyond social, just people's negative perceptions about aquaculture. It also brings in the economics. So there's a balance between sort of the positive effects of aquaculture, food security through the future, but balancing that with some of the social issues as well as the environment issues. This one is very difficult to get a handle on. It changes from place to place. Public perceptions of aquaculture differ in Nova Scotia than they do in, say, British Columbia. So it's a difficult one. Most of the science right now is This one is fairly easy to deal with. The science is really dealing with these two, and in particular, how many, what sort of biomass can you get out of a particular bay? And so that's production carrying capacity, which we'll talk about. One of the main drivers of carrying capacity is the interaction between the bivalves, the shellfish, and the food. And I'll just say right now, we're going to focus a fair bit on mussel culture. That's where a lot of the work is being done. But it's this interaction. The mussels are filter feeders. They pump water through their shells. They filter the particles out of the water. And so at some point, they're going to deplete their food supply. If you just increase, there's a limit to the food supply in any bay. And so at what point do they deplete their food supply to a degree that it affects their growth or actually affects other organisms in the ecosystem? So as well as the mussels depleting the food, there's a number of processes going on in any ecosystem that's helping to renew that food supply, and we also have to include those when determining what the carrying capacity is. First of all, it's the physical processes, the tides that replenish the food that the mussels are depleting. Water is constantly moving, so there's that side of things. There's also the production of new food, the phytoplankton. So just from sunlight and nutrients, phytoplankton are going and replenishing that food supply. So you have this balance that you have to calculate. If you're trying to determine what's the effect on the food, how much depletion is acceptable, you have to account for what the mussels are doing, the shellfish, as well as these physical factors and these other biological factors in the system. So it's not just a simple matter of looking at depletion by the animal itself. Excessive food depletion, reduced meat yields, which is directly linked to production carrying capacity. Excessive food depletion also has effects on the food web. It's other organisms that also require that food for their normal growth in the system. And so there's one more thing that goes beyond just the depletion of the food in the water column, is the production of fecal organic matter. And what does the effect that might have on the local environment, on the organisms that live underneath the shellfish cages. So we'll talk a little bit about that as well. So that's more of the effect on the benthic environment, whereas with the shellfish, we're dealing mainly with the effect on the food supply in the pelagic environment. And one of the reasons we do focus on mussels is because they are suspended up in the water column, generally for culture, and that gives them access to the food supply throughout the water column. Whereas when you're dealing with benthic culture, the potential for food depletion is much lower because they don't have access to the full water column. Just to give you an idea of the capacity of shellfish to deplete the food supply, one mussel, if we're looking at, say, a 1 gram mussel, which is getting closer to harvest size, on average, they filter about 60 liters of water per day. They really are prolific at the ability to process water, pump it through their shells, and filter the particles out of it. If you scale this up to 240 million mussels, and I'll tell you why I picked that number here in just a moment, but they're filtering 144 billion liters of water per day. So that's quite a volume that they're processing. And it just happens, taking an example from Prince Edward Island, our best guesstimate of how many mussels are in Tracadie Bay, which is the most heavily leased shellfish culture site in Canada, we calculated there's about 144 million mussels of this size in Tracadie Bay, and that's only the mature size mussels. There's also smaller ones. The bay is about 37 billion liters. Mussels can filter 144 billion liters per day, so they can process that entire bay several times a day. Of course, we're not it's a very simple calculation. We're not bringing in the physical the tide bringing more food in or primary production. But it's just to give you an idea of what mussels can actually do. Please.
I just wonder if you have any estimate of the filtration capacity for other shellfish. Is it
Oh,
similar
yes.
between mussel, oysters, and scallop? Or
No.
really
They're all different. I did a review of all three of those species a few years ago for Sandy Shumway's book on shellfish aquaculture. And they all have a high capacity. Mussels are probably, because they live in this sort of assemblage, unlike scallops and oysters, they have the highest capacity because they just live in these very dense groups. And so, individually, they have somewhat similar, filtration capacity, but it's this fact that they can live in such high densities.
Okay, so individually, we can estimate that they filter the same quantity of water.
Well, it depends on size, for the same size, yeah.
Same size,
Yeah,
three
it's
different-
similar. It's similar, but
it's not
it gets a little complex on why they do change a bit, but it is similar. So just bringing in this concept of mussels being ecosystem engineers, this is another scientific definition. A beaver is an ecosystem engineer and how they change the environment around them. And mussels are the same. First of all, because of the structures that they provide, in this case up in the water column so that tunicates can grow on them, that's engineering. But also because of their feeding ability and ability to process so much water that they've been classified as ecosystem engineers. And so that's why, this whole idea of carrying capacity, was so important when dealing with suspended mussel culture. So what we want to do is actually go out and measure how much of the food, mussel aquaculture is having, how much of the food is being removed by the culture. And so, we developed a research method. This isn't something that, the average farmer is going to do unless you married someone very wealthy. But we have these instruments that we can tow behind our research vessel here, which will measure the amount of food in the water very rapidly, very frequently. This instrument called the Acrobat, it'll undulate up and down behind our boat, and where we get our position, depth, total particulate matter, and chlorophyll A within the farm. And so we tow this instrument all in and around these suspended mussel farms just to see how much of the food is being used. And just some examples. This is a long line mussel farm here. We took our instrument and towed it along this red line. So we went through the farm and around the farm on several occasions, and we mapped the amount of particles in the water, the amount of phytoplankton in the water. And so you can see the depletion and how much depletion there is in a farm. So on this particular occasion, you get a depletion zone right in the center. This is the same farm another time where it's being depleted in a larger area, and another one depleted in the center. So we say a similar picture where the mussel populations on these farms can reduce about 80% of the food supply in a very limited area, in some of these spots. But on average, if you average it out to the whole farm, they're removing about 30% of the food that's being imported into that farm. So we do know that they can deplete, large amounts of the food. And we use this to help calibrate our models of, predictions of how much depletion there is. We've done this again at a larger scale. This is a bay here. This is actually in Spain, where we did a study at mussel rafts in Spain. It's a little bit different, but actually kind of the same as longline culture in that there's just a very large biomass of mussels up in the water. And so these show our tow tracks going in around all of these these mussel rafts in this bay. You know, we did it twice, one on flood tide, one on ebb tide, and we see the same picture, you know, with the phytoplankton being depleted inside the farms, you know, on pretty much all occasions. We do it at different depths in the farm, and you know, gives us a lot of information, but it always shows that, you know, the mussels can remove a very large amount of the food supply that's being transported through them. Getting a little closer to home, again, coming back to Tracadie Bay, always an attractive place for us to work, although we do some of this in Nova Scotia as well. Where we used our Acrobat, you can't tow it into the farms in Tracadie Bay unless you want to lose the equipment, but you can go up through these navigation channels. And this is a 4-kilometer long transect where we measured the amount of food in the water over different times of the day. And so right at high tide, there's a large amount of phytoplankton in the water, particularly in the central part of the bay. And then just 3 hours later, we do that survey over again. A lot of that phytoplankton is gone. Over 30% of that phytoplankton is gone. And that's at a time when there's no other sources of food coming into the bay. It's just the mussels removing it. So we can show quite clearly that you know, the suspended culture is having a fairly large impact on the food supply in the water column. Another way to look at food depletion, and this way is more directly applicable to industry, is to, well, first of all, this is St. Anne's Harbour up in near Sydney, Nova Scotia. It's one of the largest mussel aquaculture farms in Canada right now. It just, this is a much larger bay than Tracadie Bay. And so back, it was around 2005, I suppose, this farm was just getting going. And so we could do some work with industry there to look at how that was affecting the food supplies and how that effect on the food supply was affecting the mussels. At the time, well, St. Anne's Harbour has a requirement to do environmental monitoring at this particular site. I think it's the only shellfish site in Canada that has to do regulatory monitoring. And one of the things they monitor are the mussels themselves. Various things like, you know, what's the average yield per sock of mussel. And so they do this for every line in St. Anne's Bay. And as St. Anne's was being developed between 2004 and 2007, you know, the amount of mussels on these leases was gradually increasing over time. We could actually see what was the effect on the yields. Average sock yields declined, and the time it took to grow the mussels increased. And so this is related to the effect that they have on their food supply and to carrying capacity. As they're using up their food, it takes longer to grow mussels, and they don't grow quite as well. And so, you know, this is kind of a characteristic of production carrying capacity, is if you look at the dotted lines, this is for the 2 different leases, is that as you increase the biomass on the lease, your production initially goes up, eventually meets a peak, and then will start declining as they're overusing the food supply that's available. And so the point where you get the peak, this is your production carrying capacity, is that you're getting diminishing returns on your investment. And so there was a bit of data here over this short period of time we looked at it that seemed to fit the theoretical bell curve that we expect to see. There should be a lot more data. We stopped looking at it in 2007, so there's another decade of growth data that would be very interesting to look at someday. The point I want to make here is using this approach, sort of a trial and error approach for defining what production carrying capacity is, you actually have to exceed the carrying capacity to determine what it is. And which isn't a great thing to do, is you don't want to get poor yields. And so we sort of go beyond this trial and error approach to more of a modeling approach that will help predict at what point can you get your maximum yields. And so that's what my co-authors here, my co-speakers will be talking about. And so I think I'm at the point now where, oh, I still have a whole thing to talk about. Benthic effects, this won't take very long, but it's, again, this production of organic matter. As the animals are digesting the food, they don't digest everything. About 20% of the fecal material that comes out is organic. That goes to the bottom, and when it goes to the bottom, it decays on the bottom and can have effects on the benthos. In the Canadian Aquaculture Activities Regulations, organic matter wastes are considered as a deleterious substance, and which is regulated. Fortunately, shellfish culture is exempt from those regulations. They only apply to finfish aquaculture, unless, of course, your aquaculture site is required to have a monitoring program for site approval, which is getting back to St. Anne's Harbor and what happened there. Because it was such a large site, DFO had implemented a monitoring program on them as part of their site approval. What happens with increasing organic matter enrichment is that there's a bit of a cartoon here that explains what happens. This would be your natural community, and this is what happens as you increase the amount of organic matter going to the bottom. This is the oxic sediment near the surface, and this is the anoxic material down deeper. The community changes as you get more and more of this organic enrichment and as it's rotting on the bottom. And so you get this shallowing of the oxic layer. You get the change in the community to these opportunistic species that can live in these organically enriched conditions until eventually you get all anoxic sediment and you get white bacteria, sulfur-reducing bacteria sitting on the top, which is what you want to avoid, and that's what's being regulated. So how do you monitor this? Canadian aquaculture regulations monitor these benthic community impacts based on measuring total dissolved sulfides in the sediments. Hydrogen sulfide, as you probably know, is a toxic material. It's a byproduct of the degradation of organic matter, and it has become kind of the regulatory hammer for all organic disposal in the marine environment. So if you have too much sulfide in the sediment, you're going to have a large impact on the benthic community. And so, the regulations say, there's a certain method you have to use to do it. Recently, I have to mention this because this is research we're just finishing up right now, is we're developing new methods for improving how you measure sulfides in sediments. So, collecting these core samples, bringing them back and processing them very rapidly. Within a few minutes, we can tell you what the sulfide levels are within the sediments. And we're also developing additional indicators of the impact based on dissolved oxygen levels, just probes that we can put into the sediment, genetic diversity, microbial biomass. There's a whole slew of things being worked on right now. And the idea is to have more than one index. If you just have sulfide, you might come up with some false positives, false negatives. And so you want more of a weight of evidence from a number of different indicators of impact. And so, that's the sort of work that's ongoing right now. Coming back to St. Anne's Harbor, there was one year we went back there in 2008, did sampling throughout the bay, and you can see that within the lease that had been operating the longest in St. Anne's had higher sulfide levels, getting up to what would be a regulatory threshold if it happened to be a fish farm. Something else we did, this is over in Tracadie Bay, PEI, was we did a lot of sulfide measurements running along a line, say this is Tracadie Bay, but just a line going from inside the farm to the outside the farm. And so this would be 40 meters inside the farm to 50 meters outside the farm. And so what you see is that as you get closer to the farm, edge, which is right here, the sulfide levels go way up. And again, if it was a finfish farm, if the level had reached 3,000 micromoles of sulfide, you wouldn't be allowed to restock that farm. And you can see it went way over that at this particular site in Tracadie Bay. So just because it's a shellfish farm, we can't ignore what's going on in the system, the environmental interactions, in this case, benthic effects. They can be important, they can be significant. And because the regulations don't include shellfish culture for a lot of these things, it doesn't mean that we shouldn't be try to be sustainable.
So when you're monitoring that, I don't know, say in Tracadie Bay, how far apart the lines are, but presumably they're
5 meters.
5 meters, really.
Or is it 15? Tomas? It's been a little while since I've been there.
Anyways, when you're sampling, are you sampling directly under? Is there a difference?
In this case, no. We were just going along a couple, we actually couldn't sample right under because we were sampling using a core from the surface. So we're tied up on the line and just putting our core down next to the line.
So would you say that the waste is spreading fairly evenly over the whole bottom, or
Well,
little distinct lines along?
Yeah, it isn't all that even. It's going to be going up and down like a wave, be highest underneath. Tracadie is kind of a special issue because it's so shallow. It's only 6 meters deep. And so you don't get as much spreading as the fecal material is going. It just pretty much goes right underneath the lines. And so there is spreading. You get a storm and it moves it around. And yeah.
So you're saying on a finfish, 300,
3,000
3,000?
right there.
3,000, okay, would be the,
You wouldn't be able to restock a finfish farm at that level.
how many tons of mussels per acre? I'm just
Yeah,
wondering,
it's a good question, but
what would be
yeah.
the stocking capacity?
Well, that is sort of the definition of the carrying capacity. And I couldn't, maybe my co-speakers might be able to address that more than I could, but yeah, off the top of my head, I wouldn't even want to say.
Is there a bell curve per acre of ocean?
Yeah, and every acre of ocean is different. The physical oceanography is different, the flushing is different, the benthic community is different, the bottom type, the depth of the culture, the depth of the water. There's all of these things we have to account for. So basically, that's why you monitor, because there's some uncertainty in what the impact is actually going to be. Even though the modelers are great, there's always some level of uncertainty, and so that's why you monitor.
I also understood that for control of these impacts, having frequent biofouling, washing and things like that, frequent pressure washing, so that you don't get as many tunicates fall to the bottom at the same time, is one of the management strategies to control issues like this.
Yeah, well, that's true. And, what I've talked about has only been the fecal organic matter going to the bottom. Now you have all of the tunicates as they're being torn off going to the bottom. You've got dead mussels also going to the bottom. So, there's all of, it's, when you're actually monitoring, you're measuring all of those effects.
So you're looking for sulfide reducing bacteria?
Well, that's one way, that's one indicator, is if you see the white mats of this bacteria, then that's an indication that sulfide levels are getting fairly high and that the impact would be fairly high. I think with time, we better move on to my next speaker here.
Okay. Hi, everyone. So my name is Thomas Guyondet, and I'm a colleague of Peter, but I work in Gulf region in Moncton, where we also have a section dedicated to shellfish aquaculture and its interactions with coastal ecosystems. And for the part of my talk, I will be focusing on the physical aspects, the water circulation aspects, We just mentioned that it has importance for different aspects of aquaculture, bring food to the bivalves, and also trying to get rid of some of the waste.
Can I just interrupt you for a minute?
Sure.
Can everybody hear Thomas?
All right. All right. So I'll try to speak up.
I don't know how the mic works, to be perfectly frank. Is mic turned on?
I thought it was just for a recorder. Yeah. Yeah. So
Okay, sorry.
I'll try to speak up. So yeah, another thing about that hydrodynamic aspect is that you can look at things, and it's true for carrying capacity in general. You can look at things at different scales, different spatial scales. Peter talked a lot about the farm scale, and I'll be coming back. I'll be going back to that as well. But you can also speak about the bay scale or estuary scale of things. So I'll be talking about these two scales, and we just talked about flushing. It's the main feature that we are looking at for carrying capacity is water renewal, basically. So either to bring more food or to remove the waste. So if you look at the base scale first, as I mentioned, what we are interested in is water renewal. And you have a range of methods to estimate that renewal. And it goes from very simple methods. I'm showing the tidal prism method, we call it, on the left side here, to more sophisticated and complex methods. The reason I put the tidal prism method here is you might hear about that in some certification programs. It's an indicator that is used as a criteria for certification. The good thing about it is that it's fairly easy to calculate. You just need basic information about the bay, such as surface area, depth, and the tidal range. That would be enough to calculate that. Actually compare the volume of water that's entering into the bay at each tide and the full volume of water in the bay. And you compare these two, and you get a time it takes for the tide to renew the whole bay. The inconvenient is that it only gives you one figure, one number for the renewal of the bay. Because it assumes that the bay is just one big box of water, and that water is all well mixed. It has the same characteristic everywhere, so it's not very realistic in that sense. So that's why we move to more sophisticated methods, and probably the most detailed one is using numerical models. That's the one I'm presenting on the right here. And the idea is just to split your bay into very small parts. That would be the cubes you can see here that we call cells. And then you use a computer to calculate the water movements through these cells. And in the end, you end up with a more realistic and detailed picture of how the water is moving into your bay and how it gets renewed from outside. So I'll give a bit an example of that hydrodynamic model, as we call it. And I'm sorry again, I don't have examples of Nova Scotia embayments, but I'll be using Tracadie again as a thread of our talk. So you can see all these triangles of the cells of the model, all these small triangles, and the model will make its calculation on all these small triangles. The difficult part about this method is that it needs much more data to be able to give you an answer. And there are two categories of data, one for forcing, so it's everything you need to actually make the model work. And it goes from the topography of the bay and information of the tides outside the bay, so here in the Gulf of St. Lawrence. River discharge, if you have any river flowing into your bay. Also information about the weather, temperature, salinity, if you want to include that. The second category is validation data, and it's the same kind of, same type of data, but you would make observation of this data at different locations into your bay. And so you can compare the model results at this location in the bay with the actual data. And it's the way we use to make sure the model is working properly and also estimate its accuracy. Maybe to give you a better idea of what the model results look like, I put a short animation here. I'm not sure you'll see much, but at least the colors. The color shading is representing the water surface elevation, so it will change with tides, going from blue at low tide to reddish at high tide. And there are also arrows, but I'm not sure you'll see them, but they are showing the direction of the current, and the length of the arrows are actually representing the speed of the flow. So if it wants to work. So it's just an illustration of the model results. So the model calculates actually that water surface elevation and also the current speed and direction at each of the cells. So it gives you that more detailed representation of water circulation into the bay. And that's fast forward. It's probably a week of data, but within 30 seconds. So there's an extra step we go to estimate water renewal time from these results. But in the end, we end up with a map of water renewal time in the bay. It's actually the time it takes for water anywhere in the bay to get renewed by water that's coming from the outside. And this is a typical results for bays, coastal bays with a narrow inlet. You have a fairly good exchange of water close to the inlet, but the further you go inside the bay, of course, it takes more time for the water to reach, outside water to reach these places, and it takes more time. So it goes here, for example, from around 5 days to more than 60 days at the head of the bay. Another kind of advantage of this kind of model is their flexibility. So as I mentioned, the hard part is to get the data, the forcing and validation data. But once you have done that once, and you have built your model once, if something comes up in your system, such as, a good example is an opening in the dune, the sand dune, then you already have that modeling system. You just need to change a bit the grid of the model, and then let the computer redo the calculations, and you can see what this opening in the dune did to the water exchange and water renewal into your bay. And in this case, in Tracadie in 2010, the water exchange got almost doubled. It reduced the water renewal time by half. So this is the kind of information we can get, and what it can tell you is that if you're in a farm close to the openings, just water exchange by tides might be enough to bring you new food, enough new food. But once you get to the bottom of the bays, then you're more dependent on the local production of the food, because the opening the new water is so far away that you really need to rely on that food that's produced there. So I'll move to the farm scale now. And so at farm scale, and if we look at water circulation, one thing that's a question is what happens when you put all these structures, these aquaculture structures in the water, mostly mussel socks or oyster cages. And I'm sure you've heard about the drag effect. It's as soon as you put a structure in the water, this will affect how the water flows around that structure. And usually one of the main effects is that it slows the flow down, having structures in the water. So I'll be giving an example, using an example that comes from a mussel grower that asked us that question not long ago. He was complaining that the farm just in front of him had his line perpendicular to the main direction of the flow. And he was saying that farm is blocking all the water flow that's bringing the food to my farm. So we get to thinking about that. There are not too many studies about that circulation of water in small scale, farm scale. So that's what I represented. So represented here, two similar farms, but with direction of lines in the line in opposite directions. So that drag effect. It happens that it's actually a combination of two processes. One is what we call obstruction or diversion of the flow, and the second one is just friction. I guess the easiest one to deal with is friction from a calculation point of view, is because it's really linked to the structure, the characteristic of the structure you put in the water, so its size and its roughness. And so two similar mussel socks would have similar friction effect. So if you want to know the friction effect of an entire farm, then you just need to multiply the effect of one sock by the number of socks that there are in the farm. So if we come back to this example, both farms will have the same, or roughly the same friction effect, because there are the exact same number of mussel socks in each farm. When it gets more interesting is the obstruction or diversion of the flow. And so here you have to imagine that you're swimming in the water that comes into the farm. So that's what I try to represent here. At the bottom, it's a side view of the farm. In one case, you have the water has to go through the openings between the lines. So that would be the first sock of each line. And in the other case, it has to go through the first line, so in between the socks of the first line. So it's what causes that obstruction, and it makes a large difference between the two orientations of the lines. So just to have a rough number, I did a quick calculation of the section area that is actually available for the water to go through in both situations. And for a typical mussel farm, it gives a reduction of 30% area by having the lines in perpendicular direction to the flow. So yes, it's quite substantial obstruction. And the question is what happens when you block the flow like that? Well, water will try to find another way another place to go through. And in these situations, it's either going around the farm or underneath, if there's some space on the surface as well. And that's what actually happens. These are measurements of flow speed in a mussel farm at different depths. That's the north-south direction, east-west on the right. And what you can see is that during both the rising and the falling tide, the flow speed is increased from 0 below that 4-meter line, that is where the mussel socks end. So yes, there's actually more water going underneath the farm than if there was no ropes in the water. So there's a concept of how the physics works to explain that change in the direction of the flow and where most of the water goes through, and there are different parameters that drive that phenomenon. But and this is another illustration from model results showing that the incoming flow gets decreased a lot. Where it gets decreased the most is inside the farm, actually. But to compensate that, the flow is increasing in speed on the side of the farm and also beneath the farm. So if we come back to our mussel grower, he was right to say that that farm with perpendicular lines was obstructing, was blocking the flow to his farm. But if you think in terms of food delivery, the fact that more water, so the speed of the flow means that more water is going around the farm and beneath the farm. So less water is going through the farm, which means that that farm with perpendicular lines is actually removing less food from the water. And if you're a farm behind, you're actually getting more food than if the lines were parallel to the flow. So it's a bit an illustration of how flow around mussel farms or aquaculture farms in general can be difficult to comprehend at first. And I think I'll stop here, just repeating that when it comes to carrying capacity and hydrodynamics, it's really water exchange that's the key. And at the bay scale, you can find different places in the bay that have different exchange. But where the exchange is poor, you still have local food production to compensate for. But if you're looking at farm scale, then scale is not large enough for the local production of food to be substantial. So you're really depending on water circulation, and you want to maximize that water exchange to maximize the availability of the food.
Everybody's hungry, eh? Me too.
Just wait for the micro.
Okay, so my name is Ramon Filgueira. I'm originally from Spain, and 10 years ago I moved here to Halifax to work with John Grant at Dalhousie. And I came with the idea of using the concept of carrying capacity into management. And as Peter mentioned, the definition of carrying capacity is very intuitive from the conceptual perspective, but it's very difficult to apply to management because what is unacceptable, right? based on that, I started to dig in different ecological theories and try to find a way to bring that unacceptable to a way in which we could make this concept operational. And we found this way to represent what happens on the ecosystem that could be applied to survival farming. In the horizontal axis, I'm representing increasing biomass of shellfish in a bay. And we are going to say that the increasing biomass is causing an increasing pressure on the system. And in the vertical axis, I'm going to represent ecosystem health. And after that, I'm going to go through this concept in a way that up here we have a healthy and pristine ecosystem. So in a situation in which we don't have farming, we have, as I mentioned, a pristine ecosystem. The system is happy, performing really well. If we increase a bit the biomass in the farm, perhaps we will see a decrease in ecosystem health, but not too much. The system is still performing well. The problem is that if we keep increasing the biomass in the system, as Peter mentioned, we will reach a point beyond which, if we keep increasing pressure, the system will collapse, right? We are going to remove food, we are going to increase organic loading, etc. As you can imagine, defining this threshold is absolutely critical for regulations, because if we determine this threshold, we can say that under that threshold, the system is performing well, and above that threshold, the system is compromised. So based on this, John and I came up with a potential definition of carrying capacity. We thought that we could define carrying capacity as the stocking density of shellfish at which some measure of ecosystem health is within the bounds of natural variation. And this can sound like a mess again, right? But we thought that the use of the concept of natural variation could be very intuitive. For example, we know that temperature in Halifax in the typical month of November goes from 0 to 12, right? If this year we get a couple of days that are 25 degrees, we know that something is going on, right? The natural variation between 0 and 12 is exceeded. If we have a day at 25 degrees, we are extremely happy because it's warm. But if we get 5 or 10 days in a row at 25 degrees, we say, oh, something is wrong. We can apply the same reasoning to shellfish aquaculture. And we can apply that to a measure of ecosystem health. And as Peter mentioned, a key concept in shellfish aquaculture is food availability, mainly phytoplankton. We know that if we reduce phytoplankton, we are limiting the production of our farm because we don't have enough food to feed all those mussels or oysters or scallops or whatever. And phytoplankton is also the base of the food webs. Therefore, if we remove the food from here, the whole trophic web will suffer. So we had a target. We want to analyze and measure phytoplankton, and we had a threshold, was the natural variation. Based on the combination of both, we can bring management on board. And based on what Peter and Thomas said, there are a bunch of variables, there are a bunch of forces that are important in shellfish aquaculture sites. We have currents, we have nutrients, light, etc. So it's not easy to understand how the system works. And we can go to the system and take some measurements, as Peter did with his Acrobat. We can take a snapshot of the system. But if we want to understand what happens over time, we need to go to numerical models. And this is what I did and I do in my career. This is an example in Tracadie Bay, as you know now. In this project, Thomas ran the hydrodynamic model. Peter and John collected a bunch of data from mussels, phytoplankton, nutrients, etc. And we put everything together with a bunch of equations to predict what would happen to phytoplankton populations over time. And this is how we estimate phytoplankton depletion. So Peter went and measured things. We work on our office with computers and try to match the observation that Peter did. This is the estimated depletion in the system. This is a relative, not an absolute scale. That's important to take into account. Here we have almost 100% depletion. It doesn't mean that we don't have phytoplankton there. It's because this is a percentage and not absolute values. But this is helping us to identify the areas that could be compromised for farming, right? And based on the allocation of biomass in this corner and the water circulation in the system, the result is that this area could be compromised and farming there could suffer. I also work with Robin in St. Anne's, and we use the model in the same way. We calculated the hydrodynamics in the system. We knew where the biomass of mussels is allocated, and we ran different scenarios to see if we could increase the biomass in the system and the impact on phytoplankton. This is the current scenario, assuming that all leases were stocked. The average depletion is around 25–30%. It's difficult to see here, but hopefully in the handouts you can see it. But there are some marks around the leases showing a local depletion. If we double the biomass, you can see that depletion affects the whole system, right? And that's telling you that if we move from here to here, the depletion is going to spread and affect the whole bay and not only to your local lease. Have another example. This is in Malpec. And it's, again, to show you how we can use these modeling tools for management and to perform marine spatial planning exercises. In Malpec, there are some current leases in blue and in dark red. These are oysters, clams, and the blue ones are mussels. And some years ago, somebody, well, the government, I assume, came with the potential to explore this system to increase the mussel production. This in red, we have potential new leases in the system. And the question was, what will happen to the system and to the other farms if we grow additional mussels there? We did pretty much the same. Thomas ran the hydrodynamic model in the system. I put together the ecosystem model, and we ran different scenarios. For example, these two ones show the same biomass of mussels within the system, but allocated in different locations. Look at how this small change, like removing these releases from here, these ones, and moving them to this location can change the system. It's not a whole lot, but you have an impact on mussel growth, right? So if these leases would be affected and reduce mussel growth by 7%, we can rearrange the leases and reduce the impact. So our models allow you to do that and play with different configurations. And I thought that in addition to show you the models that we run, I thought that it could be important to show you how you can collect data in your farms to be used in the future for models or even for your farming practices. This is a complex figure, but I think that could be easily explained. In the horizontal axis, you always have the stock biomass. Basically, this is for Tracadie Bay, the tons of mussels within the system. In the vertical axis, in the left one, always the depletion, which is represented in all the panels in red. And in the right axis, you will see here the mid-yield, growth rate in terms of dry weight of mussels, and growth rate in terms of shell length. And the model predicts what Peter mentioned. If you increase the biomass, you increase depletion, and you have a detrimental effect on mussel performance. Mid-yield drops, growth rate drops. Therefore, if we are able to determine that this is a good threshold for carrying capacity, we can estimate the growth rate that we should observe in the system to guarantee that the system is performing at a healthy level. If we observe a growth rate below this threshold, it's telling us that the system is not performing well. And you can see the parallelism with this figure, right? It's the same idea: increasing pressure, increasing biomass, ecosystem health, in this case represented by the performance of the mussel itself. So the main take-home message is that if we keep track of the biomass that we have in our leases and the growth of shellfish within the leases, and we plot that over time, we can get some idea if the system is damaged, is performing well or not. And think about the parallelism with temperature. If you have a good reference that between 0 and 12 degrees is okay, you can have a parallelism with your mussels or oysters or whatever. You know that this growth rate is okay. If you have a reduced growth rate, the flag will be raised, and you can think perhaps we are exceeding carrying capacity. And I think that that's it. I try to be quick so we can eat.
Any questions for?
I have one, just very quick, and it's for the three of you, if you don't mind. We have about perhaps 3 or 4 projects that are going to need studies of carrying capacity, mostly production and ecosystem carrying capacity. And my colleague Adrian has been already started the discussions with Senefex to see if they could take on some of these projects. But after looking at your presentation, I wonder if it's something that we could also discuss with you guys, and
Sure.
And if you guys would be interested in one of those projects, or maybe 3. I mean, I don't know. It will depend, I guess. What is the process? If we are to do that, what would be the normal process to follow?
I can probably answer unless you want it to be in Spanish. And then
Either way, man, I can speak Spanish.
Es cierto.
PFO is currently negotiating more with provinces on what priorities and priority areas.
I cannot make more jokes.
The aquaculture